In order to understand BGP, we'll also need to understand the BGP attributes. BGP attributes are used for the best path selection algorithm, and they are classified as follows. We'll have well-known mandatory attributes, which must be present in every BGP update message, and they are AS-path, origin, next hop. We should have well-known discretionary attributes, and they must be supported in all BGP implementations, but they don't have to be included in all BGP update messages. We'll have local preference and atomic aggregator. We'll have optional non-transitive attributes, which are not required to be supported in all BGP implementations, and those are MED, cluster list, and originator ID. We'll have optional transitive attributes, which are not required to be supported in all BGP implementations, and if they are not recognized, they are ignored, and this is the community and aggregator. Our scope for this lecture is to know next hop, local preference, AS path, origin, MED, and community. Those are the most used attributes. So next hop. What is the next hop? It's the IP address of the peer which is sending the route. And this address must be reachable for the receiving router. So let's say we have three routers. We have the eBGP routers, we have a router which is running eBGP and iBGP, and we have a router which is running iBGP. Okay, so the blue router is sending this route to the green router 2. It is sending the next hop also, along with the route. And if we look closely, we see that the next hop is its interface address. So it will teach router eIBGP2 that in order to reach this IP address here, it should use as a next hop for this route this IP address. So in order to reach 192.1.1.1, you should send all your traffic via XE001 interface. After the E or iBGP router 2 will receive the route, if it will check if the next hop is resolvable, and only after that it will install the routes in its routing table. And here we can have two cases. And here we can have two cases. We should also know that by default eBGP is changing the next hop address for each route, and iBGP is not changing the next hop by default, and in order to achieve this you need a policy. So let's say that you didn't configure any policy for the next hop self. This iBGP peer here will try to send the route to the iBGP1. And as you can see, the route 192.1.1.1 will have the next hop of also 1.1.1.1. After the route will be shared with iBGP1, iBGP will try to resolve the next hop. And if the next hop is not resolvable, the route will be not installed in the routing table. So in order to change this default behavior, you should create a policy on the router 2. And the policy looks like this: set policy, options, policy statement, next hop self, then next hop self, and set protocols: BGP group, iBGP, export, next hop self. Basically, these two lines here, this is the policy itself, and this is where you apply the policy. Basically, this policy will change the next hop of this route. It will send the route to iBGP1, but the next hop for this route will be 10.10.10.1, which is the IP address of this interface here. After the route will be delivered to iBGP1, it will try and resolve the next hop. And in this case, this next hop here is resolvable because it is directly connected to iBGP1. So next hop is a very important BGP attribute, and it should be shared with every route, because without next hop the traffic cannot be routed successfully. We can also have the local preference, and by default the local preference have a value of 100, and you can change the local preference through a policy. Local preference is valid only within the autonomous system and it is not sent via eBGP. And a BGP router will prefer a higher local preference than a lower one. So let's check this case here. We have two ISP routers which will send the route to Google DNS server, and in the route it will state that the next hop is ISP2 for this route and ISP1 for this route. So the routes will be learned by R2 and R3. As we can see here, R2 will advertise a route with a with local preference of 200, and R3 will advertise a route with the local preference of 150. R1 will compare both routes and it will see that the route received from R2 will have a higher local preference, so it will send its traffic via R2 and ISP2. So how to configure the local preference? You configure it as a policy as we discussed, and you can have multiple filtering capabilities. In this case I stated that from every route received from ISP2 use the local preference of 200. I applied this policy to the IBGP as an import policy. I created the next hop self for R2, so the routes sent to R1 will have the next hop, the R2 router. On R3 you can also have the possibility to configure the local preference straight in the BGP configuration without using a policy. So just specify the preference of 150 in this case. On R3 I also configured the next hop self, so routes received by R1 from R3 can see that the next hop is router R3. When a route will transit an autonomous system, it will have the autonomous system address added in a form of the autonomous system string. ISPath is used to avoid loops by not importing route that have the ISPath to the local IS in the routing updates, and ISPath is also used to manipulate the best route selection. So what do I mean? Let's say that ISP2 is learning a route from router C. ISP1 is learning the same route from ISP2, and ISP1 wants to share the same route learned from ISP2, which learned from router C to router B. ISP1 will try to send this route for example to router B. When this route will be received by router B, the ISPath will be examined, and if it will see IS300 in the ISPath, it will immediately drop the route in order to not form a loop over here. Also, as I said, ISPath is also used to manipulate the best route selection. So, for example, the router C is advertising a route to ISP2. And this is the configuration which we have applied on router C. We created a IS prepend policy, and in the policy we prepended the local IS number 3 times, and we applied it as a export policy, which means that when you create an export policy, it means that information from here to here will be shared, or information will be shared from the local router to its neighbors. If you create an import policy, you can filter which information is received by the BGP neighbors. For example, router B can have a export policy configured to router C, but router C can have its import policy, which will filter information received from router B. So, for example, we don't want that ISP2 to send any traffic using this link here. So for all the routes shared from router C to ISP2, we will have the bigger ISPath. When ISP2 will see this route, it will not consider it as the best path, because probably it is learning some routes from router B, and from B side the route is much better, as we can see here. The S path is much shorter. So when comparing these two routes here, the route received from ISP1 would be better because of the shorter IS path. We also have the origin code, which indicates the origin of the route, and it can have the following values. It can have the value of I, which indicates that the routes are learned from an interior gateway protocol such as OSPF, ISIS, static or aggregate. It can have a value of E or 1. This means that the routes were learned from IGP protocol, which is a predecessor for BGP. So in nowadays, when you see a E here in the AS path or on origin code, you can know for sure that it was learned from an EBGP peer. When you have the value of a question mark or value of 2, this means that the route origin cannot be determined. We can also have multiple exit discriminator, which is used when 2 or more connections exist to the same remote autonomous system. MED is used to influence best path selection by preferring one neighbor over another. Lower MED is a better MED. MED is also an optional attribute, and if it is not configured, then it gets the default value of 0. So we have two autonomous systems, AS300 and IS15169. We have two routers connected to routers from our autonomous system. So let's say that router R2 will send the Google DNS route with the MED value of 300, and router R3 is sending the same route with MED value of 400. As I mentioned, the lower MED is a better MED. So in IS300, the route received from R2 will be considered a better route, and the traffic will be sent to R2. You can apply MED to a specific route using the Junos filtering system. In this case, it is using route filter all zeros or longer, which means that any route sent to R3 will have a MED value of 300, and it is also applied as a export policy to neighbor R3. Also have the community attribute, and the community is used to tag routes that share a common property, such as AS number, originated from a specific neighbor. They can be marked as unsafe routes. There are well-known communities on the internet, and everybody is marking the routes which are not good. The communities is a great filtering tool, and it is used for eBGP mostly. So let's say that we want to mark the routes from IS15169 with community 15169. We marked all the routes originated from R2 with community 15169. Let's see how we can use the community. For example, on R1 we have this policy here, which is saying that from community 151.169 you add the preference of 200, and you export this local preference to IBGP peer here. Also on our internal router you can use the community to accept routes. For example, in this policy here, if the route is from this community, then accept them. And you can imply it as an import policy to accept the routes on this router which are originated from AS15169. Or on R1, You can manipulate, you can add, remove, delete, replace the community for the routes received from AS15169. For example, we can configure this policy, and we can specify the neighbor from neighbor R2, insert instead of R2 an IP address, then community add, set, delete. You can change or add any community that you want. You can even delete it. And in this case, I chose to set the community of 555-200, because this is the community routes from R2, and I defined this community here, routes from R2 members 555-200. When R2 is sending routes to R1, they will have a different community set. Or I can add a community and it will be added along the community which R2 send us. Since we learned the important BGP attributes, let's see where we can also use them. So let's say that we have this route here, 192.168.0.1/28, and this route is being learned from multiple routers, and each of them is sending this route learned from different locations, and that will have the different local preference value as path, origin codes, and MED. So for BGP, when it will calculate or select the best path, the first step would be to compare the local preference on all routes that have the same destination, 192.168.0.1. So BGP will prefer routes that have the higher local preference. If there are multiple routes with the same preference, BGP will move to the next tiebreaker, which is the IS path. BGP will prefer routes with the lower IS path, and if there are multiple routes with the same IS path, BGP will move to the next tiebreaker. Now BGP will prefer the routes with lowest origin code, or let's say better origin code. And the origin codes are preferred in this order. IGP will be preferred over EGP, and EGP will be preferred over incomplete routes. And if multiple routes with the same origin code exist, BGP will move to the next tiebreaker. As you can see here, it shows these routes that they had the same local preference. These routes here that they had the shortest IS path, and these routes here that they had the lowest origin code. The next tiebreaker is the MED, and the lowest MED value is preferred. Again, if we'll have multiple addresses with the same value, then we'll move to the next tiebreaker, which is from where the route was learned. BGP will prefer the routes learned from eBGP over iBGP. If there are multiple routes learned from eBGP, then BGP will move to the next tiebreaker. The last tiebreaker is that the BGP will prefer routes from a peer with the lowest peer ID. In most of the case, BGP will not go that far when selecting the best routes. It will most probably end somewhere on the second step, because it's a very low probability to have a route with the same IS path number. Also, for iBGP, there are some additional steps that we need to take before calculating the best path. And as we saw in this section here, the route with the lowest peer ID or peer router ID will win. We can have some cases when the router ID from where the route was learned is the same. So as the next tiebreaker for IBGP is that the always oldest route will win. So in our case this was the oldest route, and it was chosen as the best route. So on a quick side note, like I said, you can find the video series links in the description, and you can watch these videos chronologically. You can also hire me on Fiverr. I offer consulting and design services, troubleshooting and whatnot. And if you want to follow along with my Udemy courses, you will also find the discount codes in the description. Thank you, and I will see you in the next one.